Okay, hi everyone, my name is Catherine, and I'm excited to share with you our group's work on porting Flash to Ookami. So just a brief description of what Flash is. The Flash Center was founded in 1997 as part of the DOE's Accelerated Strategic Computing Initiative, and Flash has been used as basically the acceptance and performance code for a lot of the machines at Los Alamos and Lawrence Livermore National Lab. And what it is a modular and extensible software package for multi-scale, multi-physics applications, which is a mouthful. So what that really means is that Flash provides you with a lot of different solvers for things like hydrodynamics, nuclear burning, gravity, high energy density physics, and you can combine them in unique ways to create your own physics application. Flash is written in Fortran 90, like a lot of physics codes, and it's parallelized with MPI. It's not successfully threaded yet, but that'll be in the upcoming version that we're excited to test. And the way that it works is you have your problem and it's put on a grid and the equations are solved on this grid. And it uses the paramesh library for adaptive mesh refinement, which I'll show you in a few slides. And you can run 1D, 2D, or 3D problems using the code. So our science application, since we're in astrophysics, is we're trying to see if we can model a really dim supernova. So instead of a normal white dwarf, we have a hybrid white dwarf, which is a white dwarf mixed throughout with metal. And instead of fantastically exploding it into smithereens, we just have it undergo the reaction that happens inside your car engine, which is called the deflagration, which is a type of subsonic burning. So I'll show you a little movie. This is our white dwarf here, and you can see it start to expand as the center heats up and the flame begins to burn through the white dwarf and the plumes expand out into space. So that went kind of fast, so I'll just play it again. So here's our star, and you kind of notice that there's a lot going on. So as the problem goes on in time, what's happening is this grid is evolving, and that means that over time, things get more computationally challenging. So we have our problem set up so that there are more grid blocks where the action is happening. So in the beginning, we have hundreds of blocks, and by the end of the simulation, we have hundreds of thousands of blocks. So a big challenge for us was getting this to fit inside the memory on Ookami. Office hours is the most helpful thing ever, like Ava mentioned in the beginning. So we had a lot of people helping us out, and we were able to do it. And then we were able to, out of the box, the GCC compiler is easiest to use. So we did a strong scaling study with our Supernova problem. And we found that we are able to scale our problem across nodes on Ookami until about 200 processors when it gets work starved. But so far, so good. Next, we wanted to see what compilers work on Ookami, because like Ava and Tony mentioned, there's no magic bullet compiler that works for everything. So our code is in Fortran 90, it's parallelized with MPI, and we tested the GCC, Cray, and ARM compilers and tried adding SVE optimizations just out of the box. So what we found is that for our application, the ARM compiler is almost 3 times slower than the other two. We also found that enabling SVE doesn't automatically produce the speedup that we were hoping for. So like Eva mentioned in the beginning, the GCC compiler can't vectorize certain math functions like the exponential function and the power function that are used throughout Flash. But you can link it to the ARM performance libraries, and Smeet taught me how to do this, so I put a little line down there so you can use it too. But we don't expect to get any speed up faster than the speed up we got with the Cray SVE compiler, because that can vectorize these math functions, and if GCC could vectorize them too by linking in the ARM libraries, we don't expect it to give us anything faster than that. So we need to go in manually and tune our code. Another interesting thing we found is that Mvapich was slightly faster than OpenMPI, and Gerard had this great idea of, well, maybe they're using different amounts of memory. So we ran this really quick memory use program. So we just initialized MPI and had the problem sleep for a while. And we just looked at how much memory it was using. So we found that OpenMPI, at least in Fortran, compiled with GCC, uses more memory than mBabbage does. And the lesson here is not, don't use OpenMPI. OpenMPI is great, and you can definitely use it. The lesson and the takeaway is that if you're using OpenMPI on only one node, it's a good idea to turn off the InfiniBand and other communication so that OpenMPI will use a lot less memory and you can use more of the memory available on a node. Something else that we tried, and this is why I was very interested in what Gerard was saying before, is that we had Ben check if MPI placement affected the runtime of our Supernova simulation. So A64FX is a NUMA node, and Flash uses mostly point-to-point communication. So we wanted to see, can we take advantage of this in the core memory groups on the A64FX? So instead of running our problem using all 192 cores on 4 nodes, he ran it on half that number and tried placing the processing elements in block or cyclic placement. So fully filling 2 core memory groups or half filling all of the core memory groups. And he found that it didn't really make a difference whether you do one or the other. But the big difference is that if you run on 96 cores on 4 nodes, it's a lot faster than if you run on 96 cores on 2 nodes, which is full subscription. And it's also almost as fast as if you use all 192 cores on 4 nodes instead of half that number. So this is kind of, I was very confused about this, but now that Gerard has seen this also, I'm kind of happy and it's not as confusing. So it might be something with the operating system, and we also have to play around with how the communication in Flash and what it's doing. Finally, we want to see how different is the performance between running on an Intel processor versus Ookami. So at the ISCS, we're lucky because we have the Seawolf cluster as well as Ookami. And we found that running the same problem with the same compiler on the same number of nodes and the same number of cores produces, you can run it in 45 minutes on Seawolf, and the fastest runtime we got on Ookami was 2 hours. So this gap is larger than expected from the difference in just the processor speed alone. On Seawolf, it's 2 gigahertz instead of Ookami's 1.8 gigahertz. So to get the most out of this architecture, we need to tune our code manually for SVE instructions and make use of the high bandwidth memory. So to do this, we did some basic profiling of our code and found that 50% of the time we are spent in the hydrodynamic solvers. And within that, 20% of the total time is spent in the equation of state, which basically for every single grid block on that picture that you saw before, it has to take in the density and energy and calculate all the other quantities like pressure and temperature in order to evolve the system. And that's very hard to vectorize because there's a lot of nested if statements and function calls and table lookups with Newton inversions. So we have to do some work to do this. One thing that we've been working on, Alan has been translating and working on code that Robert wrote, and Ava and Tony, taking Cray's PAPI profiler and basically making it into a module that you can just add to your Fortran code. So all you have to do is import this module, create a profiler object, and so you can set up different regions throughout your code so that you can profile different methods in your code or different sections of your code, so that it'll give you the results for each of them separately. Then you put in the code that you want to profile, and finally you deallocate the profiler object. And you can do this throughout your code without too much modifications. And in the end, what it'll give you is for each region, basically the number of hardware cycles that your code spent in this region and how many seconds it took to execute, how many SVE instructions you're using, the memory bandwidth, your cache misses, and things like that. So this will be really helpful, and we're planning to put this into Flash to get more detailed profiling information. So in the future, we're looking at running a pure hydro problem called the set-off explosion. And we're doing that because our code spends most of the time in the hydro module. So we're hoping we'll learn a lot. And we're hoping to find the bottlenecks by using PAPI for both a 2D and 3D problem. We're hoping to vectorize the EOS and other routines and link different math libraries to the GCC compiler to see how that will give us a speed up. We're going to study MPI binding emplacements and figure out the communication patterns and memory use of our problem. So thank you to everybody who helped us so far, especially office hours, which are the greatest thing ever. I think they're tired of seeing me there. So some of you guys should show up and come too and bring your own problems to debug. And yeah, we welcome any questions or discussion that you have. Thank you so much.
So, Catherine,
thanks a lot, Kevin.
There's a question in the chat, Catherine. How do you measure memory usage?
Oh, that is a great question that I had for a long time. And so 2 ways to do it, I think, that I know of. One is you just SSH into the node that your job is running on and you run top. And then you can see how much memory is in use. And if you cancel your job, then you see how much memory your job has used by like kind of subtracting the use when it was running from the use when you stopped it from running. And another way is I wrote a tiny program that basically looks in, oh gosh, what is it called? proc/processor ID. There's like files for all of those. So if you SSH into a node, open up all those files, you can add up the RSS value for every process that's running your program, and you can add up the RSS value for all of those, and that'll tell you like how much memory your program's using.
And I think you made this also available to all the users in the Slack channel, so everybody can just.
Oh yes, it is on Slack.
Thanks. I'm working on a similar problem, and we use the second approach of reading proc and things like that. So yeah, I think this is a big question for Fortran users in general.
Okay.
See, you can just call get our usage system call, but not Fortran.
And then also, just real quick, I'd like to say thanks to Doug Swesty for helping with the Fortran to build the modules for the PAPI calls.
Just a quick note about the memory problem. In Slurm, you can actually use SEF, S-E-F-F, with the job ID, and it gives you all kind of information, including memory utilized.
Can you say that one more time? Seth?
SEF, S-E-F-F, like that.
Oh, cool. That's good to know.
You could type that in the chat.
Yeah, I just
there we
did.
go.
Minus the
Fantastic.
capital.
Okay, so just lowercase. Okay.